It's 3 a.m. on March 15, 2025, in the CMS detector's control room at CERN, nestled beneath the French-Swiss border. The air hums with the distant thrum of superconducting magnets, and a team of physicists huddles around a glowing display. An algorithm, sifting through a torrent of proton collision data from the Large Hadron Collider, suddenly flags something extraordinary: Event 847,293. Two muon tracks materialize 43 centimeters from the collision point with no visible ancestor particle. No tracks leading back to the beam. Just a ghostly particles appearing out of nowhere, carrying a whisper of something unseen. Across the screen, 268 gigaelectron volts of energy vanish into the void, pointing to an unnoticed party. Dr. Sarah Chan, the shift leader, sets her coffee down untouched. "Run the cosmic ray filters again," she says. Her voice calm, but her eyes locked on the display. The operator's hands slightly tremble. "Already checked. This isn't cosmic." The room falls silent, save for the hum of air conditioners. This moment could rewrite physics. Welcome to the hunt for dark matter, a chase that's been decades in the making. And today, we're diving deep into a potential breakthrough that could alter our understanding of the universe. Let's start with the stakes. Dark matter makes up about 27% of the universe's mass energy, 5 times more than the typical material that forms stars, planets, and us. It's the invisible support structure that holds galaxies together, shaping the cosmic web that spans billions of light years. Without it, stars wouldn't cluster and galaxies wouldn't exist. Yet, for all its influence, dark matter remains maddeningly elusive. It doesn't emit, absorb, or interact with light or normal matter in any meaningful way, except through gravity. For 80 years, scientists have hunted it in underground particle detectors, space telescopes, and collider labs like the LHC, chasing a ghost that's always just out of reach. Until now, every experiment has come up empty. Until the evening of March 20th, 2025, when CMS caught something that doesn't fit the standard model of particle physics. Those to muons, appearing like apparitions, could be the first direct evidence of a dark matter particle decaying in a laboratory. So, what exactly happened in that detector? When protons collide at nearly the speed of light in the LHC's 27 km ring, they release a fire hose of particles. Most follow the rules of the standard model, the framework that explains the fundamental particles and forces of our universe. But Event 847,293 was different. The two muons appeared 43 centimeters from the collision point, suggesting a heavy particle was created, traveled a measurable distance, and then decayed into invisible muons. The missing 268 gigaelectron volts of energy points to particles that escaped detection, carrying momentum into a hidden realm of physics. This signature, called a displaced vertex, in addition to lacking transverse energy, is the holy grail of dark sector physics. It's what theorists have predicted for decades: a particle from a hidden dark sector briefly crossing into our world, leaving breadcrumbs we can see and ghosts we can't. The CMS detector's upgraded trigger system, designed specifically for Run 3 to catch such displaced muon pairs, worked flawlessly. It spotted what older systems would have missed. To comprehend the significance of this, let's zoom out. The standard model is a triumph of physics, explaining everything from the behavior of atoms to the fusion in stars. But it's incomplete. It doesn't account for dark matter, which we know exists from astronomical observations. Galaxy rotation curves show stars moving faster than visible matter can explain. Gravitational lensing reveals invisible mass-bending light from distant galaxies. The cosmic microwave background bears the imprint of dark matter's gravitational pull. Yet despite this evidence, we've never caught a dark matter particle in a lab. Detectors like Lux Zeppelin, buried deep underground and filled with ultrapure liquid xenon, wait for dark matter to nudge atomic nuclei. Space telescopes like Fermi-Lot scan for gamma rays from dark matter annihilating in the galaxy's core. Colliders like the LHC try to create it by smashing protons together. All have come up empty. until this anomaly. The CEMS event fits theories of a dark sector, a hidden family of particles with their own forces, connected to the rest of the universe through rare interactions, possibly mediated by a dark photon or a Higgs boson portal. Let's examine the research that supports this event. When the LHC smashes protons, it produces a zoo of particles, some of which decay almost instantly. But in event 847,293, the particle traveled 43 centimeters before decaying, implying a lifetime of about a trillionth of a second, long enough to stand out. The missing energy suggests something invisible carried away momentum, consistent with WIMP's weakly interacting massive particles, a leading dark matter candidate. The symmetry of the event is striking, muons appearing at the same distance with missing energy pointing in opposite directions. It's too clean to ignore as noise. The CEMS team ran every check in the book. Cosmic rays ruled out. The muons originated inside the detector. Beam halo particles eliminated. Timing matched stable beam conditions. Detector glitches none. Every sensor cross-checked, no errors found. The event survived a gauntlet of tests, each intended to eliminate false positives. The likelihood that this is a statistical fluke is less than 1 in 50 million, but science demands more than one event. Replication is key. The Atlas detector, the LHC's other major experiment, was scoured for similar signatures. By morning, their team was in an emergency session combing through data. If Atlas is of the same mind, same pattern of displaced muons, same flight distance, same missing energy, it's a game changer. Real physics replicates across independent experiments. Flukes don't. Beyond colliders, the hunt extends to other fronts. Underground detectors like Xenont and Lux Zeppelin could catch dark matter particles from space scattering off nuclei, resulting in brief flashes of light. Their no results so far constrain the interaction strength of any dark matter candidate, but a CEMS discovery would guide their search in space. Fermi-Lot and upcoming telescopes like AMIGO could spot gamma rays from dark matter annihilating in the Milky Way's core. If their signals match the collider particle mass, we'd have a three-way confirmation: colliders create it, underground tanks catch it, and telescopes observe its destruction. The theoretical repercussions are mind-boggling. If this event holds up, it points to a dark sector, a hidden valley of particles with their own forces barely touching our world. One possibility is a dark photon, a force field similar to the regular photon but for dark matter. It could travel centimeters before decaying into muons, matching the CEMS signature. Another theory involves the Higgs boson, discovered in 2012. It may serve as a gateway to the dark sector. The Higgs could occasionally decay into dark particles, producing missing energy and displaced vertices. Recent Atlas and CEMS data limit the Higgs invisible decay rate to about 13%, a strict limit that any dark sector theory must respect. More exotic models propose entire cascades of dark particles, a hidden valley where particles decay sequentially, resulting in multiple displaced vertices. Each theory makes testable predictions, and the LHC's upgraded detectors are now sensitive enough to catch them. 3 major upgrades were carried out by the LHC beginning in 2022, bringing a new superpower to CEMS: displaced muon triggers. These catch muon pairs appearing centimeters to meters away from the point of collision, a feat impossible in earlier runs. The high-luminosity LHC, set to begin in 2029, will take this even further with high-granularity timing detectors, stamping tracks with 30 picosecond precision, faster than light crossing a proton. This will confirm whether the muons came from sequential decays or random noise. Other experiments are joining the hunt. Phaser, for 180 meters downstream from ATLAS, catches particles like dark photons that travel far before decaying. A surface detector called Methuselah, above CEMS, targets particles that drift hundreds of meters. SHIP, planned for the 2030s, will probe ultra-weak couplings in beam dump experiments. Together, they form a surveillance network covering every corner of the theoretical dark sector map. Let's address a common misconception. Isn't dark matter just a placeholder like dark energy or the ether of old? No, dark matter's evidence is concrete, from galaxy dynamics to the cosmic microwave background. It's not a fudge factor, it's a physical substance we can't yet touch. The CMS event isn't proof of dark matter, but it's a tantalizing clue. If it's real, it's not just a particle, it's a new sector of physics. Imagine discovering not just a new element, but an entirely new periodic table. The technological fallout could be profound. Quantum mechanics, once an abstract curiosity, gave us MRI scanners and transistors. Dark sector particles could lead to new sensors, imaging technologies, or even computing paradigms, though the path is unpredictable. Decades ago, no one foresaw that nuclear physics would lead to cancer treatments. Dark matter's applications could be just as transformative, but they start with moments like this. So, where do we go from here? The CMS team is analyzing more data, aiming to replicate the event. ATLAS's results are pending, and their confirmation would be huge. The LHC's high luminosity will yield 10 times more data, sharpening the signal or exposing it as a fluke. Underground and space-based experiments will cross-check any collider findings. If this signal holds, textbooks get rewritten. If it fades, we learn more about our detectors and tighten the search. We are getting closer to cracking dark matter's code. This isn't just a science story, it's a human one. Dr. Chen and her team, fueled by coffee and curiosity, are part of a global endeavor to unravel the universe's deepest secrets. They're not chasing fame, they're chasing truth, one data point at a time. This is why particle and space physics captivate us. It's not just about particles or equations, it's about our place in the cosmos. Dark matter isn't just a puzzle, it's a reminder of how much we still don't know. That event at CMS, those Timuans from nowhere, could be the first step toward a new era of discovery. So, what do you think? Dark photon, Higgs portal, or something wilder? Drop your thoughts in the comments, hit that like button if you're as excited as I am, and subscribe to stay with this story as it unfolds. The universe is talking, and we're finally learning to listen.